Hey guys, so let's start the definition for the ellipse, okay? 10.3. All right, the first definition is the ellipse. An ellipse is the collection of points in the plane whose distance from two fixed points these two fixed points are also known as the foci, add up to a constant number. Okay. Now the foci are two fixed points on the interior of the ellipse. Okay. So you guys remember the parabola had one focus, okay? Now the ellipse has two foci, which is two of them. So what does that mean by these two definitions? Let me just give you a little picture in which we will probably draw a lot more pictures in a little bit. So let's call this foci 1 and foci 2, okay? And it's made up of, and it says here, a collection of points. I mean, every single exterior here, these are all points that's made up that's collected to make an ellipse, okay? Then it says, collection of points in the plane whose distance from two fixed points. So let's say I'm gonna pick that point, this distance, and that distance, okay? If I add those two, let's call that should be the same as if I were to pick this point and add that with that, okay? So the distances in red, if you add those two distances, should be exactly the same as the two green distances. And let's say I want to pick this point. From here to there should be the same as if we would from here to here. They should be on the same exact line because the two foci should be on the same exact horizontal line. But because I don't want to draw it on the same one because you can't see, but this distance here from foci 1 to this dot here on the right side, add that to focus number 2 to the same dot. That should be the same exact distance as the red and as the green. And if I want to go further, we can even make, okay, well, what if we want to make this dot? With that distance plus that distance, all of those distances, when I add them up, the blue should equal the red should equal the green should equal the black. So that's what it means to be an ellipse. Okay, so that's the definition of the ellipse. With the two fixed points, which are called foci. Okay, if you take the distance from the two foci to any point on the ellipse, and you add them up, they should give you the same constant. All right. Major axis. Let's move on to that. Is the line containing the foci. So that's why earlier I said the focus 1 and focus 2, the two foci, should be on the same line. So this is now called the major axis, okay? All of that right there. Focus 1, focus 2, so two foci, same major axis, all right? Minor axis is the line through the center and it's perpendicular to the major axis. The center is the midpoint of the major axis, major axis, or minor axis. Okay, so the minor axis, if we use the same picture, is going to be goes through the center and is perpendicular to the major axis. So here's the center right there. Okay. Vertices are 2 points of intersection of the ellipse and major axis. Okay, so what do I mean by that? So the vertex are the 2 points of the ellipse, which is the outer, and where the major axis is. So those are vertex 1, vertex 2, together they're called vertices. The length of the major axis is the distance from one vertex to the other vertex. Now, normally, I would ask you to use your electronic device to define the whispering galleries, but I'm just going to give it to you in this set of notes, okay? Whispering galleries are domes that are constructed in a way so sounds produce at any certain point are clearly audible at another location. And we need to know this fact because this will be used in our application later, okay? Now the next 3 vocabulary, I'm going to draw a picture and then I'm going to define them at the same time, okay? All right, let's go draw this picture. So here is an ellipse. Pretend it's a perfect ellipse. Okay. So we have an ellipse. I'm going to get a different color. Let's say that you have a planet here orbiting around. So the planet is going to orbit around the sun. Let's make the sun right here, okay? Around the sun in an elliptical shape. And I'm going to make the sun, there you go. All right, so let's go and define this. Aphelion, when a planet is farthest from the sun. So what it means is this. If you look at this planet, okay, so currently I have it drawn in green, but as you know, it orbits around the sun in this elliptical shape, and it moves here and here and here. So when it is over here, like here, okay, then that is the furthest location from the sun. So we call this distance right here, students, from the green to the sun, aphelion. Okay. Next is perihelion. When a planet is closest to the sun. Okay, so as it's orbiting around the sun, and again, this is not drawn to scale, okay? If it's over here, then this distance right here is the closest to the sun. It's not drawn to scale, so do not hold my ellipse to that. But so when it's at the two vertices, it's really where we're measuring it to the sun, okay? Since I can't draw to scale since it's by hand. So this blue distance from the sun to vertex number 2 here is perihelion. So I'm going to spell it right here. All right. The mean distance of a planet from the sun. So just so you guys already know, the mean distance means the average. So the mean distance is the length of the semi-major, which is semi means half, axis of the elliptical orbit. Okay. So if we look at the major axis, okay, so here's the major axis from here all the way to here, from one vertex to the other. So the mean distance is half of that. So let's make the center. Let's pretend the center is right here in the black. So the mean distance is from here, one vertex to the center. This is the mean distance. Okay. So the mean, 2 of the mean distances, okay, is going to equal aphelion plus perihelion. All right. Let's go on and do the theorem. Theorem number 1 here. Equation of an ellipse. When you have the center at 0, 0, so let's draw that out. Center at 0, 0. Major axis is along the x-axis, so let's make it super y, vertex 1, vertex 2. And then that means the minor axis is going to be above here, since the major axis is on the x-axis. Let's draw this out really quickly. Now from your activity, you guys by now should know a couple of things. You guys should know, and again, not to scale here, okay? That the foci should be on the x-axis as well, since the vertices are on the x-axis. Then the distance from the center to one of the foci is going to be called letter C. So here is C. The distance from the center to the minor axis is called B. Then the distance, if we were to make this triangle, just like that, this is a right triangle. Since the major and minor axis are perpendicular, this is now called A. So let's fill out a few things. We will have the foci at plus or minus C distance from the center, and the y is still at 0. The vertices are going to be plus or minus A distance from the center, and the y-axis is still 0. We can also go and label these points here. This should have been labeled 0, comma B. This down here is 0, comma negative B. Over here, all the way over here, yes, that's also A, comma 0. So let me draw that out again in red. Remember, A is the hypotenuse of the triangle, but this distance right here from here From the center, the vertex is also A. Over here, this vertex 1 is negative A comma 0. Okay. So let's go and write a standard form of our equation with the center at 0, 0. It's going to be y squared over a squared, since it is positioned horizontally. So the a squared is going to be the biggest value. So the x variable gets the a squared, plus y squared over b squared equals 1, where a is the biggest number out of the ABCs. So A is going to be bigger than B, and both of them will have to be positive, which is greater than 0. Now, based on a Pythagorean theorem, since A is the largest value, it's going to be B squared plus C squared equals A squared. Okay? And the major axis, it's on the x-axis. All right, that's what it says right here. All right, now let's go and do the next theorem. This one says the center is still at 0, 0, but now this time the major axis is on the y-axis. So this is more vertical. Okay, so this is 0, 0. Now I'm going to make a dot here. So let's call that vertex 1. Vertex 2, we will make the minor axis shorter. Let's draw this out. Okay, so very similar to the horizontal position earlier. Then if we know the vertices are on the y-axis, then we will have focus 1 here, focus number 2 here. Let's draw it out. Now from the center to the focus, it's always C. I don't care what you guys do, it's always C. Then center to the minor is always B, okay? So that leaves us, this last distance is going to be called A, always. No ifs, ands, or buts about it. Let's label some points. From this point is going to be B comma 0. This point over here is negative B comma 0. Now again, remember, from the center to this vertex is totally not drawn to scale based on this letter A. But that is going to be 0, negative A is the A distance, same A distance as this guy. Okay, just be very, very mindful. I know I'm not drawing it to scale, but that A value is the same A value from the hypotenuse of your triangle. Then up here, this vertex number 1 is going to be 0, comma A. Okay, let's fill out. You will have the foci going up, so that's going to be 0 plus or minus C. You have the vertices, 0 plus or minus A. Okay, the standard form is going to be, since the y square, okay, now since it's positioned vertically, the y square would get the A square, because the A value is always bigger than the B. Then that means this gets a B square, and it must always equal to 1, where A must always be bigger than B, and both values must always be positive. And again, similarly to the previous theorem, it's going to be C squared plus B squared equals to A squared for the Pythagorean theorem. And again, this is only when it's vertical, where the major axis is on the y-axis. Okay, so what if we have an ellipse that's not at the center? Similar, except that we are going to call the center H comma K. So, oops, I don't need a highlighter, so I need a pen. Okay, so both center are no longer at the origin. Let's call it H comma K. We'll draw the first one with the major axis. It's parallel to the x-axis. Let's draw it out, okay? Let's make the center right here, H comma K. And let's make this vertex right here. Vertex 1, vertex 2. Not to scale at all. And let's make this a minor, just like that. Okay. All right, let's draw it out. So normally when I talk about ellipses, I call this horizontal. So that means this is your major axis. So focus 1, focus 2, let's just fill that in. Okay. Now when you look at the foci, as you can see, it's moving along the horizontal, so only the x values will change. So from the center, you're going to take the h, which is the x coordinate of the center. You will either add a c value, which let me label that for you. This is c, okay, or minus c to get to focus 1. So you add plus or minus c. Now the y value does not change from the center. Now let's talk about the vertices. The vertice from the center to the focus, from the center to the vertex is the letter A. So here's the center, here's the vertex, the whole green piece is A. So again, you can take the h value, add A to get the vertex 2, or minus A to get to vertex 1. So we're going to take h plus or minus A, comma, k. Your standard form equation, because it is positioned horizontally, we're going to go, okay, the x variable will get the a square. Then that means, oops, I'm writing too big. Okay, this one I'm trying to squeeze in. Oh, nope, still too big. All right, let's squeeze that in to fit in the box. So x minus h quantity square will get the a square, plus y minus k quantity square will get the b square equals 1. And again, the b square, okay, let's write it plus c square, it's always a square. That is the Pythagorean theorem that you have to use. So what's a b? B is from here to here, and a is this guy right here, since this is the right triangle. Okay, let's move on to this guy here. The h and the k is still not at the origin, call it, we're gonna still say the center. Let's make this right here, okay? H, comma, k. We will say that the major axis is going to be parallel to the y axis. Okay, so let's go up here to say vertex 1, down here to say vertex 2. So the minor axis, let's make it short here and here. Let's draw that out. All right. So first box says the foci. The foci would be here, focus 1 and focus 2. As you can see, the h value is not changing, only the k value is changing, right? The y value of the coordinate changing. So we will say, okay, well, h is not changing, we'll keep h as is. The k, if we add a c value, it will give us f1. If we minus c value, it will give us f2. So from here to here is c. So plus or minus c. All right, now the vertice is very similar, except we would need an a value. So again, remember, the vertex to the center is an a distance, okay? A distance. And just to remind you, the b distance is from the center to the minor. And so that means I'm going to use green. From here to here, it's a. And that's always perpendicular. So, same thing, we're going to go h, comma, k plus or minus a, and the standard form. X minus h quantity square over plus y minus k quantity square, and it always equals to 1. Now, because it's vertical, that means the y will get a square, and that means the x's now get b square. And again, same Pythagorean theorem, b square plus c square equals a square.